Hello students, I am Dr. Yasha Tayal from ABES Engineering College, Ghaziabad. Today we will discuss about superconductivity. In my previous lecture, we have discussed about basic introduction of superconductivity and various parameters about the basic condition for superconductivity and Mesner effect. Superconductivity has a strong dependence on critical field. Superconductivity, which means zero resistance, this superconductivity will disappear if the temperature of a specimen is raised above its critical temperature, or a sufficiently strong magnetic field which is above Hc, it is a critical magnetic field value. If a value above this critical field is applied to the specimen, then again resistance will reappear and material will lose the superconducting property. So we can show this variation with respect to temperature in Kelvin and the critical magnetic field. Under this observation, we can observe this type of pattern observed. Here we have critical value. So above critical temperature and this is the value of critical magnetic field at 0 Kelvin. So above this, the material lie in the normal state. So any material which can have zero resistance below critical temperature, so that material will have certain value of resistance if temperature is above critical field or a value of magnetic field is above Hc0, then the material goes into the non-superconducting state where resistance reappears. Now, if the temperature is below critical temperature and the magnetic field is below certain critical magnetic field, which we term as Hc0, then the material is in the superconducting state. So this is the region in which material lie in the superconducting state. So the minimum value of applied magnetic field necessary to restore resistivity or to destroy the superconductivity nature is known as critical field. So this critical field is dependent on temperature. So this is basically function of temperature. The variation of critical magnetic field with respect to temperature can be represented by the empirical formula HCT is equal to HC0 1 minus T by TC whole square. So here Hc is the critical field at a particular given temperature T in which we want to calculate is the maximum value of field strength at 0 Kelvin. So basically the 0 is 0 Kelvin. T is the operating temperature at which we have to determine the volumetric magnetic field, and Tc is a constant value for a particular specimen. C0 is also a constant value for a particular specimen. So if the value, we want to determine the volumetric field in this region, 0 to Tc. So this is for a particular temperature T. The value lies between 0 to Hc0. That is the maximum field strength value. Now next we need to know what is persistent current. So persistent current is basically steady current which flows through a superconducting ring without any decrease in its strength even after the removal of the applied magnetic field. So the current which ideally lasts for infinite time, for long, very long time, over the long years, which remains, is persistent current. So this concept can be explained on the basis of Mesner effect. In this case, we need to take a hollow sphere, hollow material. So this part is basically solid part. So this is basically a ring. With the help of a ring, we can explain this. So this is the hollow part of that particular specimen. We need to plot 3 diagrams. So these are 3 identical diagrams. So in this, we will take First of all, we will take the example of when temperature is greater than critical temperature. When temperature is less than critical temperature, the last diagram is also for the same condition. Here, we are keeping the specimen in an external magnetic field, which values non-zero. Here, we are keeping again the material in the same condition magnetic field, and in the last magnetic field condition value is changed to zero. So what happens when we apply a superconducting material at a temperature greater than critical temperature, field lines can pass through the specimen. As the material is in normal state, it is not diamagnetic in nature, all field lines can pass through this specimen. Now, when we reduce the temperature below critical temperature, material behave as superconducting material, which also has the property of diamagnetic nature. So field lines are not allowed to pass through this solid part. So field lines are excluded from the solid part. From hollow part, the field lines can pass. And from this hollow part, again, solid part, the field lines are expelled. As a material in the superconducting state, it is diamagnetic in nature. Now, temperature is again still less than critical temperature, and external magnetic field is removed. So these field lines which are outside the specimen will vanish. Now the field lines which are inside the specimen are maintained. These field lines are trapped in this hollow part of this ring type structure. So why does this happen? Because as temperature is below critical temperature, certain current is developed inside the specimen. A certain current is developed inside the specimen, which traps the field lines which are in this hollow part. Now, when external magnetic field is removed, as there is still a network of current in this specimen, so the field lines are not allowed to vanish. So because of this current, an induced magnetic field is produced, which is equal and opposite. So they does not allow these field lines to move as the external field is removed. So we say that this persistent current is ideally forever, and this remains even after the removal of external field, and this value of current does not decreases in its strength. Next, there are basically two types of superconductors, type 1 and type 2 superconductors. Type 1 superconductors are also known as soft superconductors. These are known as soft superconductors. So their behavior can be shown here in this graph, where we will plot the graph in between the magnetic field and magnetization. So the behavior of material is in this form. So at a particular value of critical magnetic field, above this field, material is in normal state. So a material which can show superconducting behavior. So above critical field, material is in normal state, means resistance will be there and Meissner effect is not followed, which means field lines will be allowed to pass through the specimen. But as the critical field is below critical field, material goes into the superconducting state. Here, Meissner effect is completely followed, which means magnetic field lines are not allowed to pass through the specimen. We term this superconductor, we term type 1 superconductors as soft superconductors because this value of critical magnetic field is very low. So this value is around 0.1 Tesla. So because of this, the material is known as soft superconductors. There is no mixed state. It is a pure element. So type 1 superconductors are generally from the pure elements or periodic table. So here I have mentioned certain like aluminium, which is a pure type 1 superconductor. It has very low value of critical magnetic field, 0.0105 Tesla, mercury again 0.041, indium 0.0281, lead 0.0305, zinc 0.0504 Tesla. This is the value of critical magnetic field, which is type 1. These all are pure elements from periodic table. While our type 2 superconductors, they have a bit of higher value of critical magnetic field. Again, we will plot a graph between magnetic field and their magnetization behavior. So in this particular specimen, we found a non-linear graph. So here we are having three regions in this particular pattern. This is HC1, lower critical magnetic field, and this is HC2, upper critical magnetic field. So above HC2, material is in normal state. So a superconducting material which has the possibility of zero resistance below critical temperature. So that material, if placed in a magnetic field above HC2, will have its resistance reappear. Material will not be in this, and material will not obey the Meissner effect. It won't be diamagnetic. Now, if we decrease this value of magnetic field below HC2, this state is known as our vortex state, or we term it as mixed state, or we term it as intermediate state. So in this state, what happens is that field lines, some of the field lines are allowed to pass through the specimen. So Meissner effect is not completely followed in the region between HC1 and HC2. So which means that there will be some amount of resistance in the specimen. Now, as the critical magnetic field is reduced towards HC1, so as the region lies between 0 to HC1, Meissner effect is completely followed, which means that now it is perfect diamagnetic in nature. In between lower and upper critical magnetic field, the element is in the state of where Meissner effect is partially obeyed. And above HC2, Meissner effect is completely violated. So in this region below HC1, material is a perfect superconducting state. In between HC1 and HC2, material is in intermediate state or mixed state. So these materials have the value of very high value of HC2, which is over 30 Tesla. So that's why these materials are termed as hard superconductors, because they are able to retain the value of superconductivity at higher value magnetic field. So these are termed as hard superconductors. Now these materials are generally made from a combination of elements, that they are made from alloys or compounds. I have listed certain examples of type 2 superconductors like niobium tin, which is having a higher magnetic field, 24.5 Tesla. For type 1, we can find out the magnetic field was 0.01, 0.04. So this is about 1,000 times higher, 1,000 or 10,000 times higher than the previous value. Niobium germanium, this has 38 as the upper critical magnetic field value. Vanadium germanium, it has 2.08 critical magnetic field. Niobium aluminium germanium, that is even more higher, 44 Tesla. Niobium aluminium, that has 32.4 Tesla. So as we use a combination of transition elements or metals, then the critical magnetic field, or previously I've shown the critical temperature value, can rise, which makes more applications, more utility of these superconductors in real scenario. So type 2 superconductors can even be shown with respect to temperature also. So I'm going to plot here graph between temperature and critical magnetic field. Here we have 0 Kelvin. So this is the TC. So above TC, material is no doubt in the normal state. So material which shows superconducting state, its behavior will be above TC, will be in the normal state. This is HC1 lower critical magnetic field, and this is HC2 upper critical magnetic field, and region between these two magnetic field shows your vortex state, which is your intermediate state. So this is very important part. And here the material is in total superconducting state. So you need to remember vortex state in somewhere is even termed as the third category, but that is not a category. It is part of type 2 superconductors. So vortex state or intermediate state is the position where Meissner effect is partially obeyed. It is partially obeyed in this region. And below HC1, Meissner effect is totally obeyed. Above HC2, Meissner effect is totally violated. So these are the references which I have taken for this particular content for this lecture. Thank you so much for patiently watching this lecture.